This is Team 1072. I'm Max Bobbin.
I'm John Laporte.
I'm Catherine Wraback, and our coach was Dr. Neha Raikar. We are all affiliated with the University of Maryland, Baltimore County, and today we will be discussing our approach to solving Problem C. Just to recap, Problem C discussed the use of misinformation and censorship over social media platforms. The reason this is important is because social media platforms are a primary source for information for most people, and the sharing of misinformation is very dangerous over these platforms, and censorship is one method that can help reduce misinformation. Our approach to this problem and modeling misinformation was actually modeling it as disease. We looked at the SEIRS model, which is a set of differential equations that was used to model the spread of disease. And our goal was to use SEIRS as a basis in order to model misinformation with censoring technology. To introduce SEIRS, the model, there's the four equations that you see on the screen. And these have many parameters which describe how disease is transferred. You have a susceptible population represented by S, an exposed population, an infected population, a recovered population. You also have additional parameters that reflect natural birth and death rate, infection rate, immunity loss rate, latency period, recovery period, and death by the disease, all related with those four equations. We were then able to apply the SEIRS model to the spread of information, where, for example, as you can see, the susceptible population in our model would represent people who haven't picked a side to stand on with respect to like an issue. The exposed population and the affected population were both represented by people who have been exposed to misinformation. A dead population are represented by people who are entrenched in their belief of misinformation. An infection rate is represented by misinformation exposure rate. Recovered populations are people who accept the true information, and the latency period is the time to accept or reject a piece of information. So we assumed that over the time period that we modeled, the population of internet users doesn't change much. And while the population of internet users increases by about 4.8% every year, it was discovered to be negligible over our time span. And we also assumed that when people believe a side, that they won't change their mind later on. And finally, we assumed that in the beginning, the transfer rate of true information and misinformation is equal, but we will see later on that they do change as time goes on. And finally, a few more alterations that we made to the SEIRS model was to combine the exposed and affected terms because they represented the same population of people who were exposed to misinformation. And then we also modeled the spread of true information separate from the spread of misinformation. And then we added a factor, the censoring factor, that represented the effect of censoring posts about misinformation. And this term decreases over time as people will find a way to sort of subvert around the censoring. And then finally, we allowed dead people who believe in one side to contribute to the spread of information. And now I'm going to turn it over to John to discuss the model with no censoring.
Thank you, Catherine. So we had 5 different differential equations. We have ds dt, which is the change in the susceptible population, dem dt, which is the change in people who are exposed to misinformation, det dt, which is the change in people who are exposed to true information, and then dm dt and dt dt, which represents people who believe misinformation and people who believe true information. Some other parameters that we have are alpha, where we have alpha m, which is the exposure rate for misinformation, and this is a logarithmic relationship based off of the population of people who believe misinformation and true information. And we assumed this because people who believe the misinformation are then going to try to spread that misinformation, and people who believe the true information are also going to try to spread the true information. Some other terms that we have is we have alpha naught as our base exposure rate, delta as the pondering period, or the period that it takes for people to either accept or reject the information. We have f as the fraction of people that do accept that information. And then finally, we have n as the total population. So here is a process diagram that helps better visualize how this process works. First, people start out in the susceptible population. Then they either get exposed to true information or misinformation, in which case they enter ET or EM. then based off of the fraction of people who believe it, they either might not believe it and return back to the susceptible group, or they will believe it and then move into either the true information category or the misinformed category and become certain of their beliefs. So here are our results with no censoring. For this simulation, we assumed delta T0 and delta M0 to be 1/3 days, which is saying that it takes around 3 days for them to make their decision on if they believe or reject the information. We assumed our alpha T0 and alpha M0 both to be 1/2, and we assumed our fraction that believe it or for both true and misinformed categories to be 25%, which means 75% move back to the susceptible category. We assumed that 98% of our population starts out in the susceptible category, and that 1% starts either in the true category or the misinformed category. It's also good to note that our M0 and T0 were both assumed to be 2, and this is so that the logarithmic relationship of our alpha in our exposure rate would work with the logarithmic relation that we assumed. And now I'll turn it over to Max to talk about our censoring model.
Thank you, John. First, we looked at the effect of deleting posts that contains misinformation. We assumed that this would directly limit the exposure the susceptible population had to misinformation as it applied to our model. We defined K as the censoring factor, which represents the fraction of posts that get censored. K is a function of time and decreases as time goes on, representing people circumventing the censoring techniques. Eta is defined as the maximum censoring efficiency because even in the beginning, the algorithm won't be able to censor every single post. Finally, Z is defined as the subversion factor, which represents how quickly or slowly groups can subvert the censoring. Looking at the new model, our censoring factor is multiplied by the exposure rate, which in effect counters the exposure the susceptible population has to misinformation. Looking at the graph, we can see that all the parameters from the original model were kept the same, and for the censoring factor, the max efficiency was set to 90%, and the subversion factor was set to 2. Here, we can clearly see that while people are still being exposed to and believing misinformation, it is dwarfed by the amount of people that are accepting true information, as we would expect. Next, we looked at how flagging a post that contained misinformation differs in its effect from just deleting it. Here, the assumption was that flagging didn't directly prevent exposure, but those who were exposed had a higher chance to reject the misinformation and return to the susceptible pool. The censoring factor K looks similar to the previous definition, but a new term H is added. H represents the fraction of people who will heed the warning and reject the misinformation. We anticipate that even if flagged, there will be some people who will still accept the misinformation. Looking at our model now, the censoring factor is multiplied by the acceptance rate, which in effect counters the amount of people who are accepting misinformation and returns them back to the susceptible population. We can see from the graph that we still see the same thing in our graph, a large amount of people accepting true information, but we see more people accepting misinformation than we did with just flat out deleting it. Here we used an H factor of 0.7 and kept all other variables the same from the previous models. In conclusion, we can see that the deletion of misinformation, if done in the same way with the same factors as flagging, is about 10% more effective than flagging and 28% more effective than with no censoring at all. We also see that the exact numbers applied to the model will change on a case-by-case basis, and this is assumed to be similar to what we see with disease modeling, which change based on the disease and the seasons and the time. We also expect that in our future, we'll want to fit these parameters through experimental data, and we expect to get that experimental data from social media analytics. Finally, we can see the reference where we saw the SEIRS model and use that as a basis for building the model that you saw here today. We'd like to thank all of you for listening in. We'd also like to give a quick thank you to Dr. Raikar, who was our amazing mentor during this, and to the University of Maryland, Baltimore County, who sponsored us competing in this competition.